Good day to you from Chem Help ASAP. This video is a review of many of the common solvents that students encounter during a two-semester sequence of Organic Chemistry 1 and Organic Chemistry 2. The list of solvents covered in this video is not comprehensive, but it should include the most common ones. Your instructor may like some different solvents. If I've left out some important solvents, just let me know in the comments section and I will try to make another video. Finally, this video is intended to be a review and is recommended for students who have already learned some organic chemistry as opposed to beginners to the subject. What do solvents do? Solvents dissolve reagents in a reaction and provide a medium for the reaction to occur. A medium in which all the reagents can collide and do chemistry. For the most part, organic reactions require all the reagents to be in the same phase. That's the solution phase, and the solvent forms the medium for the solution. This discussion applies to homogeneous chemistry, everything in the same phase. There are heterogeneous reactions, but they are less commonly seen in organic classes. There is no official way to categorize solvents, but I'm going to sort solvents into 6 categories. First are the polar protic solvents. These include water and alcohols. The polar aprotic solvents include DMSO and DMF. There are very many different ethers, but the most common are diethyl ether, often just called ether, and THF. The halogenated solvents include dichloromethane or methylene chloride as well as chloroform. Hydrocarbon solvents include hexane and benzene. Ethyl acetate, a very common solvent, does not fit well within any of these categories, so I put it in an other class. If you walked into an organic laboratory and opened a solvent cabinet, you would very likely see bottles of many of these solvents. All are very common. Let's work through these categories and try to identify general trends for how they are used. Let's start with the polar protic solvents. These are water and then various alcohols. I'll include methanol, ethanol, propanol, and T-butanol. There are others, but these are representative examples. All of these solvents are somewhat reactive because of the OH groups. Therefore, these solvents are generally incompatible with the strongest acids or bases. Because different alcohols can have different R groups off of the OH, it is easy to fine-tune the polarity or non-polarity of the solvent depending on the needs of the reagents and reaction. The polar protic solvents are among the best for providing solubility for salts, and many reactions do require having salts in solution. Here are some representative reactions that are often performed in water or alcohols. E2 reactions with alkoxide bases are often performed in alcohols. SN1 solvolysis reactions, literally solvent cutting, very often use polar protic solvents, which help to stabilize carbocation formation, and the solvent is weakly nucleophilic to attack the carbocation. Aldol condensations are often performed in alcohol solvents. Of course, hydrolysis reactions, like this saponification of an ester to a carboxylic acid, very often are performed in water. Sometimes you might add a second solvent, a co-solvent, to help dissolve the starting material if it is not soluble in water. In contrast to the polar protic solvents are the polar aprotic solvents. DMSO, dimethyl sulfoxide, and DMF, dimethyl formamide, are 2 examples. These are polar and therefore water miscible like alcohols. Their polarity can provide some solubility for salts. Because they lack an OH group, they are less chemically reactive, but they are far from inert. There are many polar aprotic solvents. Other examples include acetonitrile, acetone, and nitromethane. These are less common as reaction solvents, but you do see all of these from time to time. Here are a couple reactions that use polar aprotic solvents. The SN2 is a classic. The polarity of the solvent allows solvation of anionic nucleophiles without having an OH group to tie up and add steric bulk and basicity to the nucleophile. Many palladium catalyzed couplings involve polar aprotic solvents. The solvent solubilizes the variety of salts that are required for the reaction. Ethers are very common solvents. The all-time classic is diethyl ether, normally called ether, and THF, which is a cyclic ether. DME is less commonly used, but not rare by any means. DME is a diether, dimethoxy ethane. Ethers are less polar, though THF and DME, for that matter, are water miscible. Ethers are very weak acids and therefore are often used with strong bases and strong nucleophiles. Here are two reactions that often use ether solvents. LDA, a very strong base used to make enolates, typically has THF as the solvent. Grignard reagents are traditionally formed in ether as the solvent. The Grignard is stable in ether and can be reacted in subsequent steps. The halogenated solvents include methylene chloride, also called dichloromethane or DCM, and chloroform. As solvents, methylene chloride is far more common. It is not miscible in water. Halogenated solvents are especially resistant to oxidants and strong electrophiles. The last two items on this slide are not related to their use as reaction solvents. Halogenated solvents are sometimes used in liquid-liquid extractions, i.e. during reaction workups, because halogenated solvents are more dense than water. Also, chloroform deserves special mention, as deuterated chloroform, CdCl3, is a very common NMR solvent. Here are two representative uses of methylene chloride as a solvent. The top reaction is the acylation of an alcohol to form a tosylate. Reactions of acid chlorides, as well as tosyl chloride, are commonly performed in methylene chloride. Ozone is a very powerful oxidant that reacts with many solvents. Methylene chloride resists reaction with ozone and is therefore a good solvent for an ozonolysis. The hydrocarbon solvents include aromatic solvents like benzene, toluene, and xylene, often collectively called BTX, and alkanes like hexane and cyclohexane. These solvents are insoluble in water and very poorly dissolve polar compounds. The aromatics especially have higher boiling points and therefore allow higher reaction temperatures to drive slow reactions. In some instances, the properties of benzene and toluene allow the removal of water during a reaction. Here are two examples. At the top is a thermal rearrangement. This reaction requires a lot of heat, and chlorobenzene, a substituted benzene, is a higher boiling solvent that can allow this reaction to be performed. Below is a dehydration reaction to form an enamine from a ketone and secondary amine. This reaction uses something called a Dean-Stark trap, which allows removal of water during the reaction to drive the equilibrium to the enamine product. Let's look at how a Dean-Stark trap works. Here is a simple diagram for how this reaction is set up. So the ketone, amine, and toluene are mixed in a reaction flask that is heated. As the reaction occurs, water is formed in the reaction. With heating, water and toluene boil off together in a mixture called an azeotrope. So the vapor released from the reaction mixture contains both toluene and water. The vapor rises up the glassware and into this apparatus. This is the Dean-Stark trap. The vapor eventually rises out of the trap and will be cooled and condensed in a condenser, which is not shown. Now we no longer have vapor, but solvent, liquid solvent, immiscible, toluene, and water. The solvent drips back into the trap. The water, which is more dense, sinks to the bottom of the trap, and excess toluene overflows and returns back to the reaction. In this manner, water is removed from the reaction as it forms. Finally, we have reached our other solvents. There are many other solvents, but the most notable solvent we have not mentioned is ethyl acetate. Ethyl acetate is not a common reaction solvent. It has poor water solubility. It also is a weak electrophile, so it's not good for use with nucleophiles. Ethyl acetate is actually most often encountered in chromatography and performing TLC analyses as a mobile phase, especially in combination with hexane. That was a whirlwind tour of different solvents in organic chemistry. Solvents are rarely highlighted but play a very important role in the success of a reaction. Thank you for watching until the end. Please leave a comment, leave a like, or subscribe to the channel. Take care.